Uh, Hello everyone, I'm Harsha from the University of Washington, and today I'll be talking about the system called iPlane that I've been building with my advisors Tom, Arvind and Arun. So the basic motivation for our work is that today there are several instances where it's useful to know what exactly is the performance you get on some parts of the internet. For example, in certain applications such as P2P applications, you'd like for clients to connect to peers that would provide them good performance. On the other hand, ISPs would like to know what exactly is the performance clients should receive when they connect to their customers. But the problem is right now there is no good way really to predict performance on any path unless you actually use the path. And the reason this is a problem is, I guess, known to all of you out here, is routes in the internet traverse several ISPs, and so there is no single point in the network where you can predict performance between any two end hosts. Further, though any ISP can control routes going out from it, it does not really have control over incoming routes, and so there's path asymmetry out there. And further, both routes and traffic workloads change over time, and you don't really have any static estimate that you can make on path performance. So to address this problem, given these challenges, we have built this system called iPlane. In a nutshell, what it does is it predicts path properties on the internet between any arbitrary source and any arbitrary destination. And the way it does so is we have control over a bunch of vantage points around the internet from which we continually issue measurements. And based on measurements from these vantage points, we not only predict, we predict path properties such as latency, loss rate, and bandwidth along paths that we have not even measured. And so currently we have this system continually measuring the internet daily from several locations around the internet, and all this data that we gather is available online at this URL. So first, let's look at a high-level overview of how iPlane works. So as I said, we have control over a few several vantage points around the network. So right now we have Planet Lab nodes in around 200 locations, as well as around 500 public traceroute servers. So from these few hundred vantage points, we issue trace routes daily to all prefixes in the internet. And based on these measurements, we build up this topological map of the internet. And once we discover all pop level links out there, we partition these links into access links at the edge and links in the core, and separately measure properties of these links such as loss rate and bandwidth. So this map of the internet that we build up, annotated with link level properties, we call this the Internet Atlas. And we basically use this atlas to predict properties between hosts that we don't have control over. So let's see how exactly we do that. So say there is some source and destination between which we want to make an estimate, and we don't have control over either the source or the destination, so we don't really know the path between them through the internet. All that we have is control over a few vantage points, and from these vantage points we have performed trace routes to some representative destination in the same prefix as S and the same prefix as D. So the thing we capitalize on is that by composing segments of these measured paths, for example in this case by composing SI and ID, you can get a path that is pretty similar to the actual path. So in this case, one candidate path for the path between S and D is SID, which though not identical to the actual path is pretty similar. Though the challenge here is there are several other intersections possible between our measured routes, and we have to choose among these candidate paths as to what exactly is the right path between S and D. And the way we do so is by using several properties of how routing works. The fact that BGP tends to prefer shorter AS paths, and that many people do early exit routing. So we use such properties to infer the path between any source and any destination. So to estimate the path properties between S and D, we basically use this technique to predict the forward path first, then predict the reverse path, and then compose the properties of the links on these predicted paths to infer end-to-end latency, loss rate, and bandwidth. So here's one particular example of how our path prediction works. So I was in Rio last year for the Internet Measurement Conference, and when I was there, I did a trace route from the hotel in Rio to the web server of the US Embassy in Romania. So the map on the left basically shows the actual route from Rio to Romania as given by traceroute, and the RTT measured by the actual traceroute was 298 milliseconds. And the map on the map on the right shows the path predicted by iPlane between the same source and destination. So you see that though the path is not exactly identical, it's pretty similar to the actual path. And since it's pretty similar, even our latency estimate is close to the actual value. To evaluate our path prediction more rigorously, what we did was we considered our atlas of the internet to be comprising only measurements made from Planet Lab, and used this atlas to estimate paths measured from public traceroute servers, around 500 of which we use. So this graph essentially shows how well our path predictions work. The x-axis is the AS path dissimilarity metric, which is basically a metric we use for comparing two AS paths. All that you need to know is when the metric is 0, both paths are identical. And the y-axis is the cumulative fraction of paths. So here you see that for around 2/3 of the paths in our evaluation set, we are able to predict the AS path perfectly right. So given that our path predictions are reasonably accurate, we then evaluated how well our estimates of path properties such as latency and loss rate are given our path predictions. So here are graphs plotting these estimates. The graph on the left plots the accuracy of our latency estimates. The x-axis is basically the absolute error in our latency estimate compared to the actual latency, and the y-axis is the cumulative fraction of paths. Similarly, the graph on the right plots the accuracy of our loss rate estimates. So in both cases, you see our estimates are reasonably accurate but not perfect. And to diagnose this, we further broke down our path set into two partitions. One for which one set of paths is those for which we actually were able to predict the AS path perfectly right, and the other for which we were unable to predict the AS path correctly. So we see that our estimates for properties such as latency and loss rate are significantly better when we do get the AS path right. So our hope is that as we improve our measurements to improve our mapping of the internet, and also our technique for path prediction, our estimates for these path properties will improve further. So now that I've told you that, hopefully convinced you that the data that iPlane gives is reasonably accurate, how exactly can you access this data? So firstly, all the measurement data that we gather daily is available online at this URL. And further, we also run a query server on this host, which exports two interfaces. One is a Sun RPC interface, and the other is an XML RPC interface. So you can basically issue queries for any source destination pairs you like. For example, suppose you want to determine what is the performance some set of clients out there receive to your customers. You can basically input those source destination pairs as a query, and you get back predictions of what exactly is the pop level path on each of these source destination pairs, and also what is the latency and loss rate estimates along these paths. So currently we have one query server running on this host, and we are planning to host a few more query servers at UDA pretty soon. So one interesting result we have found while doing our evaluations is that our estimates of path properties are significantly better when, suppose you want to estimate the path properties for some particular source destination. Our estimates are significantly better when we have access to a few paths from the source. And the reason for this is that there is path asymmetry out there in the internet, and the outgoing paths from the source are not necessarily reflected by the paths we measure into it from our vantage points. So in fact, in our experiments with public traceroute servers, we have seen that by just adding 10 paths from each server, we can get significant improvement in accuracy of our estimates. So it will really help if you guys can host more traceroute servers out there. We can basically scrub the web page on our own and include those in our measurements and give you better data from iPlane. So right now we also have a interface by which our query server can accept traceroutes as input, and all that you need to do is upload the raw output of traceroute to a TCP server. And even that is documented at the URL. So in summary, today I presented a system called iPlane that we have built, and in a nutshell what it does is gives you predictions, approximate predictions of paths as well as path properties between any to end hosts out there in the internet. And if any of you are interested, if any of you think this information from iPlane is useful and you are interested in using it, please drop me a mail. And also if there is any other information you think iPlane should provide, I would be glad to hear. Thanks.